So in this video, we're going to learn a little bit about average atomic mass. And you can actually find average atomic mass right on your periodic table. It's right here. So that's the average atomic mass of krypton here. The units are atomic mass units, so that's that little u. That's just a given on your periodic table. They don't write the units in, but you can know that that is the unit that's there for all those average atomic masses. And what the average atomic mass is, it's actually just a weighted average. So just like if I'm calculating the final grade for someone in a course, I'm going to weight each assessment differently. So I might weight the exam a little bit more, maybe project a little bit less, all little assignments in there, different weightings. Right, I'm going to add up all the grades, but I don't just add them all up and weight them equally. They're weighted by how much, in the case of a course, how much I think they should contribute and how much I think they should be worth for your final grade. So for isotopic abundance is the weighting factor for average atomic mass. So isotopic abundance means how much of each isotope actually occurs out there in nature. So every element has different isotopes that it can exist in, and then there's just different amounts out there in the world. So for example, copper exists in two states. It can exist in the state of copper 63 and copper 65. And most of the copper that we find out there in the world is found in the copper 63 state. In fact, 69.2% of copper is found in that state, and the rest is going to be found in the copper 65 state. So let's record this information here. Here we've got it in, if we put it in a little chart, it might make it a little bit easier. So we'll make a chart with our isotope, with the mass, and with the abundance, the isotopic abundance, just so we can stay organized about everything. So the isotope copper 63, that has a mass of 62.93 atomic mass units, an abundance of 69.2%. As soon as you see a percent with these kinds of questions, we got to convert that to a decimal. Percentages aren't very nice to work with mathematically, but decimals are great. If you remember how to convert percentages to decimals, all you got to do is divide by 100%. And you do that by sliding the decimal place over 2 spots to the left. So that gives me 0.692. So 69.2% is, as a decimal, 0.692. All right, let's do our next thing that we've got here. The next isotope of copper is copper 65. So copper 65, its mass is 64.93 atomic mass units. The abundance, it doesn't say what the abundance is. But we happen to know that there's only 2 isotopes of copper. And that means that all of the copper in the world that we know of is either in the form copper 63 or copper 64. So if 69.2% of it is in the form of copper 63, well, then the rest must be in copper 65 form. So if I do 100% minus 69.2%, that should give me how much is in copper 65 form, which is 30.8%. So that's the isotopic abundance of copper 65. It's the rest in this case. So that's my chart with all the information. Now, some elements have more than 2 isotopes, right? And in that case, you just keep going here. You could just keep writing them down. Maybe there'd be a copper 66, and you'd write down its mass and its abundance if there was more. In this case, there's not, right? But if there was, you just keep going. Then to do a weighted average, all you have to do is multiply the masses by the abundances as a decimal. So the formula here is really straightforward. We're going to say mass average, that's that weighted average, and it's going to be the mass of each isotope times its abundance in a decimal form. So the first isotope, copper 63, has a mass of 62.93 atomic mass units. So that's that first mass there. And then I'm going to grab that first abundance, the abundance of copper 63 as a decimal, 0.692. And then I add the next one. The next one is copper 65, and it has a mass of 64.93 atomic mass units. And we multiply the mass by the abundance as a decimal, which is 0.308. And then if there were more isotopes, I would just keep going. I would just keep on adding and etc. But there's not here. There's only 2 for copper, so I'll stop there. Toss it into your calculator, and I get 63.5 atomic mass units. So that's the average atomic mass of copper. Let's look at another example. It's a little bit trickier. So what if we're given the mass of each of the isotopes? So gallium-69 has this mass. We're going to definitely need our chart here. So the isotope, the mass, and the abundance. Our little chart. I might need more space for the mass. I'll move that over. So first, the isotope is gallium-69. Its mass is 68.9256 atomic mass units. And then we've got gallium-71, and it has a mass of 70.9247 atomic mass units. And then we have the average, right? Like what this all adds up to. So the average mass is going to be 69.72 atomic mass units. And you can read that one right off the periodic table. So that's from our periodic table for that average atomic mass. But then how would I find out those abundances? Well, this is tricky because there's 2 of them and it seems like I got 2 variables. How could I solve for that? Well, whenever you're solving for something, it's good to give it a name. So let's call the isotopic abundance of gallium-69 X. And then because we know that gallium happens to have only 2 isotopes, then we know that the abundance of gallium-71 has to be the rest, right? So if X was, say, 0.3 or 30%, then gallium-71 would have an abundance of 0.7 or 70%. In other words, the abundance of gallium-71 is going to be 1 minus X, or 100% minus the abundance in the percentages, but 100% as a decimal is the number 1, right? Think about 100%, making that a decimal. Take your decimal place here, slide over 2 spots, and you get the decimal just 1, right? So that's how that conversion works. All right, now we've got just one variable. The variable is X. So this is maybe something I could solve. So we set up our formula. Our overall formula is that the average mass, so mass average, is going to be the mass of each isotope. So the first isotope, gallium-69, has a mass of 68.9256 atomic mass units, multiplied by the abundance. And we don't know the abundance, so we just call it X. And then our next isotope, 71, which has a mass of 70.9247 atomic mass units, times its abundance, and we know that its abundance is the rest. So if X is the abundance of gallium-69, 1 minus X is the abundance of gallium-71. Now all I've got to do is solve for X. Oh, but I've got it in 2 places, so I'm going to have to do some collecting like terms, put on your algebra hats, and let's go for it. Replace the average mass here with what we know it is, which is 69.72. And let's simplify this out a little bit. So I'll just write this without the brackets because I don't need them. Here I'm going to use distributive property. So let's distribute this guy in here. So the 70.9247, first thing I'm going to do is multiply it by the 1, the first thing in my brackets. Well, that just makes 70.9247. The next thing I'm going to do is multiply it by the negative X. When we do distributive property, we multiply by the sign in front of the thing as well. Sorry, I made it look like a plus there. I didn't mean to. So we're going to multiply by that negative X. So it'll become negative, and it'll become negative 70.9247X. Right, it looks like we need to do some collecting like terms. So I'll keep the left side the same for now. And on the right side, well, this is a constant here, so I'll write that 70.9247 out again. But then I'll collect these like terms, right? This has an X with it, and this guy has an X with it. So let's add those together. 68.9256X minus 70.9247X. that equals negative 1.9991x. Early on this stage, keep lots of decimals so you don't make any rounding errors. And we'll round things off at the end, but not yet. So just keep tons of decimals for now. But we need to get all the constants on one side, all the x's stuff on the other side. So let's take this 70.9247 and we'll move it to the other side. To do that, we need to subtract it, right? So 69.72 will be minus the 70.9247. We're subtracting it from both sides is the algebra process that's happening there. And then on this side, we'll just be left with that negative 1.9991x. Subtracting those two things gets you negative 1.2047. That equals negative 1.9991x. And then we're going to want to clean this up, get rid of the negative 1.9991 in front of the x by dividing both sides by that number. So let's do that division. Make sure you divide by the negative sign as well. So that kills the negative 1.9991 in front of the x and leaves me just the x on its own, which is what I want. Do that division on your calculator and I get 0.6026 equals x. So remember, that's the isotopic abundance of gallium-69 here as a decimal. So if x is equal to 0.6026, then I want to convert that to a percentage. So the percentage conversion would just mean slide that decimal to the right by 2 places, and I'll get 60.26%. So that's the abundance of gallium-69 right there. And if I wanted to know the abundance of gallium-71, well, that's pretty straightforward. All I have to do, so let's see, abundance of gallium-71 is just going to be 100% minus the 60.26%, right? It's the rest, it's everything else. Because there's only 2 isotopes of gallium, it's just going to be everything else will be in the other form. So we do that subtraction, and I get 39.74% as the isotopic abundance of gallium-71 there. Now, if there was more isotopes of gallium, not just 69 and 71, but maybe a third, then we'd have to have a little bit more information to solve it. We'd have to know the percentage abundance of at least one of the 3 in order to solve it from there. But that's 2 examples that I hope will help you in your finding of average atomic masses.